Good afternoon.
Good afternoon.
Sir. Good afternoon. Good afternoon, Professor.
Good afternoon. Thank you so
Good
much.
afternoon, Professor Albert.
Good afternoon. I hope everything is going good. Let me...
All perfect, thank you.
Except for the attendance, of course, of the students. We're suffering from that.
Oh, yes, I agree. I agree. And
Very
I
low
believe that
attendance.
we're going to continue suffering because of this. I mean, probably it's an effect of Ramadan, but also students are ready to find excuses, you know.
Yeah, and late attendance. So they come, but they come at the end. So it's just not working. It's difficult.
Okay. Thank you so much for your attendance. And I will just wait 2 more minutes and then start our session today. Today's session is going to be about t-tests, or in other words, student t-tests and ANOVA. I will try to first to present you the concepts. Actually, I will start with the hypothesis testing, how we understand or what is hypothesis, very shortly, very concise summary, and try to explain the t-test and the ANOVA test with the examples, hopefully. So I will try to go a little bit faster, but if you really, anywhere is unclear, anywhere if you have any questions, please stop me and ask your questions, because I have a, let's say, a lot of slides, and I also would like to actually, if we have time, do a couple of tests using SPSS as an example again, after I covered all the subjects. So
Hello, good afternoon.
Sorry, good afternoon. Good afternoon.
Good afternoon, Professor Albert.
So just to remind you and give you a kind of heads up, so and waiting for 2 more minutes, by the way, during this time. Again, today we're going to talk about t-tests and ANOVA analysis. And then the next session is going to be about regression analysis, actually. And if we can conduct the last one, it's going to be about structural equations modeling and how we do. And again, based on the time and everything, I will try to cover the confirmatory factor analysis using Amos, also a side product of SPSS, IBM SPSS. So these are the following actual training sessions. Any questions before I start? Okay, and I believe this session is being recorded. Yes, I just checked and confirmed. So if any one of you has an urgent thing or something to do, you can also check it after the session. It's going to be recorded and will be shared with you. Okay, my dear colleagues, let me do you see my screen, my PowerPoint?
Yes.
Yes, Professor.
Perfect. Perfect. So let me start. As I said, today's session is going to be about student t-tests and analysis of variance, which also called as ANOVA. And before going in the details of these 2 different types of tests, I would like to talk a little bit about hypothesis testing, because these 2 tests actually a kind of hypothesis testing that we end up after our literature survey and everything. Then, as we discussed before, we formulate our research questions, and then from the research questions, we come up with our hypothesis. So what is a hypothesis actually? Just to remind you, a hypothesis is a claim about a population parameter. These are examples or a population proportion, either a mean or, for example, the mean in this university is GPA is 2.58, or the mean is expenditure in Kuwait is 150 KD per month. So these are the example hypotheses that we can use today's test, by the way. I mean, a hypothesis can be related to regression. For example, we can claim the relationship between two variables, of course, or effect of a variable on the other one. These type of hypotheses are examples of correlation or regression, which I'm going to cover in the further or following session. That's why I chose the examples today that we use t-tests or ANOVA tests. So in all hypothesis tests, actually, we have a null hypothesis or hypothesis 0, as we show on the screen. That hypothesis is the claim to be tested. It's always a population parameter and always claims that the means are equal or the relationship is not significant. It never changes, by the way. So always our null hypothesis is going to be if we compare some means of two groups or more than two groups or two parameters, or if we claim a relationship, the null hypothesis always says that the means are equal or the relationship is not significant that we claim. So just keep, please, this in mind. And then we have the assumption that null hypothesis is true. It's like the notion in law. I mean, of course, I'm not an expert in this one, but in law, you know, there is the innocence until proven guilty, right? So this is the null hypothesis. Everybody is innocent. But as a researcher, in that one, as a prosecutor, you claim that it's not true, so there's a crime or there's a guilt to be proven. And then in the research terms, as a researcher, we claim that this assumption is not true and we want to test it. So this is how we formulate and test our hypothesis actually. So the null hypothesis actually refers to the status quo, or again, or historical value, saying that or claiming that with the assumption that it is true. At the end of the tests that we are going to conduct, of course, we may or may not reject the null hypothesis. So depending on the status of rejection, we are going to conclude based on the hypothesis that you will see through the example. So our purpose is to see, are we going to reject or are we going to not reject the null hypothesis at the end of the tests? So how we are going to test the null hypothesis actually? This is a very simple example. Of course, we have a population, and the population has a parameter that we don't know exactly, we just assume, right? For any variable. You can claim that the population has a GPA, you can claim that the population has an age, you can claim that the expenditure, you can claim anything regarding the population. But those numbers, the means of the population, actually is a parameter we don't know exactly. If we can reach all the population, of course, we will know exactly. But based on a lot of things, based on the resources, mainly the time and the effort and the money and a lot of things, it's most of the time, it's impossible to reach all the population. So that's why we have a sample. We can reach a sample, and we have means and the standard deviations and all other parameters from the sample. Using the sample mean, try to estimate the population mean. And how do we know if we have a right sample or if we really can estimate the population? Then we use the tests, right? Let's say that we choose a sample. Let's say that we are trying to do a test or hypothesis regarding the mean age of the population. And then, as in this example, the population mean, we assume that is 35 based on the statistics, based on the historical values, based on some. And we have a sample, and from the sample, our mean age was 22. So the question is here, is this 22 really shows that the population is not 35, or did we really make a mistake and we have the 22 just by chance, so that the mean population age is really 35? So to be able to claim these two, or to be able to conclude this, we are going to hypothesis testing. And in this hypothesis testing, our null hypothesis is going to say that, because as we just mentioned, null hypothesis always says the means are equal. So our null hypothesis is going to say that yes, population mean is 35, is equal to 35. But we, as a researcher, we have an alternative hypothesis, which is exact opposite of the null hypothesis. So we are trying to test if the null hypothesis is true, or we reject the null hypothesis and accept the opposite claim. So this is how we conduct the hypothesis testing, actually. So the point is, okay, 22 is a little bit far from 35, right? As in this example. Let's say that the population is normal distribution, which based on the central limit theorem, it says that if you have the chance to get an infinite number of samples, at the end, the distribution of the sample means is going to end up with the normal distribution. So as an assumption, we assume that the population, data in the population is distributed in the form of normal distribution. And the mean is 35 for this example. But our sample is 22. So, okay, 22 is very different than 35. But this does not enough. The fact that it's different from the population mean doesn't mean that we accept that it is different. So it is far, but the question is, how far is enough to reject the null hypothesis? So this is actually a critical question for us to make the conclusion. So is it enough for us to say that no, it's not equal to 35, or it's not enough for us to claim that, so that we will accept the assumption that yes, the population mean is equal to 35. So that how far is actually a critical value of a test statistics. Test statistics creates a threshold value for us to make a decision. And this threshold value actually gives us, the claim gives us the result. This difference between the sample value and the population value is enough for us to make this decision to accept or reject the null hypothesis. Actually, this is what happens in hypothesis testing. And when we do it in SPSS, for example, we don't see these rejection or acceptance regions, but actually what is done behind the scenes by the software is actually this. The software calculates these critical values, and if the values is, this is actually two-sided test. We have a region that we accept the null hypothesis, and if the test value is in the rejection regions, we are going to reject the null hypothesis. This might sound a little bit now flu for you, but when we do our examples and everything, I'm sure that you are going to understand much better what we are talking about. Actually, I mean, I also have to say that I can spend one whole hour to talk about this hypothesis testing and everything, but due to the time restrictions, unfortunately, I have to go a little bit faster, as I just mentioned before. So the main idea, let me try to summarize. Main idea, actually, we have a null hypothesis and we have a sample in our hands. The point is the value that we get our sample. We are trying to test if it's supporting the null hypothesis or not. To be able to make a decision, we choose a test, and the test lets us to calculate the critical values and then compare our test value to the critical values, and based on the result, we decide if we reject null or accept the null hypothesis. Let me start with the tests for today, and while making the examples, I'm sure that you're going to get the idea much better. So we will start with the t-tests, or in other words, student t-test, actually. A t-test is a statistical test that we use to compare the means of only two groups or the means of two variables. Okay. So just keep in mind, if there's a comparison between two groups or two variables, then we are going to use t-tests. If our groups or the number of variables are more than two, then we are going to conduct ANOVA tests that we are going to cover today after we finish with the t. So again, the t-tests actually is used to compare the means of two groups or the means of two variables from the same population or from the same group. Before going further, I would like to mention three important points, which are the assumptions about our data to go forward with the t-test, actually. Because t-tests is an ANOVA test, and also on top of them, the Pearson correlation test and the regression test that we are going to cover later on are called parametric tests. For the parametric tests, actually, we have a couple of assumptions. The first assumption is the data, actually, of the samples are independent than each other. So each data is chosen independently than the other. And the second assumption is actually, as we just mentioned, we assume that the population is normally distributed when we consider all the data. And if we compare the groups, we also have another assumption saying that the variance within each group is similar to the variance to the other group. So we call it homogeneity of the variance. And the thing that I'm going to mention now is not an assumption, actually, is a requirement. So to be able to go further with the t-test and ANOVA test, the data should be measured in either interval or ratio level. So we have to have numbers in our hands. If your data is categorical or ordinal, we have to go with the non-parametric test, which will be covered hopefully in other sessions if we can plan. But to go with the t-test, ANOVA test, and the regression and these all parametric tests, your data should be either interval or a ratio level, which is a numerical value. So just to keep in mind this one. For the t-tests, actually we have three types of t-tests that we can conduct. These are independent sample t-tests, paired sample t-tests, or one sample t-test. So as a graphic, maybe it might be better understood. Paired sample t-test, actually, we are talking about the same group, but two different variables of the same group. Let's say, for example, if you want to investigate if there's a difference within a group between 2 points in time. Let's say that we have a group of students. We want to try to compare their midterms and their final exam grades. The group is the same, but the variable is actually belong to the same group, but we are comparing two different means. One is midterm, the other is final. We call it paired sample t-test because samples are paired. We are talking about one group. In independent sample t-test, actually, now we are talking about two different groups. So if we try to understand whether there's a difference between two different groups on the same variable, then we will conduct independent samples t-test. Let me give you an example. If you want to understand if there's a difference between, let's say, GPA of the girls and the boys, so two different groups, it will be an independent sample t-test. Or if you want to understand, let's say, average of a course between marketing students and management students, then it will be an independent sample t-test. So again, we are talking about two groups, and we are investigating a difference on a variable. And then there is a third type of t-test, which is one sample t-test. One sample t-test, we have only one group, and we want to compare a variable mean of this group to the mean of the population or to a standard value that we want to compare. Let's say, again, let me give you an example. If we want to compare the average grades of, let's say, a statistics course of our bachelor students with university average 60. So in this example, I want to compare the mean of a course grade with a standard value or a population average. So this is one sample t-test. In this one, there is one group, but again, comparison is between two values. One is the mean of the group. The second is a standard value or a population. So this is three different types of t-tests. And again, I want to highlight once more, all types of t-tests compare two groups, either two variables. So I want to start with the one sample t-tests. I want to continue. I would like to explain it a couple of, and then I would like to give you example in the slides, and then go for it. So again, one sample t-test goal is to compare one group mean with a standard value, or again, a mean of a population. Doesn't. So we assume that the groups are related from the population and independent, and the data is independent than each other, right? So, and then they don't affect each other when we create the value. So our null hypothesis for this one, of course, is going to say that if you look at the issue as two tails, it's going to say that, yes, our group mean is equal to this value. And we would like to test that putting an alternative hypothesis. As I mentioned, alternative hypothesis is just the opposite of the null, which is if null hypothesis says it's equal, alternative says it's not equal. Or we can also mention that the difference is equal to 0, or difference between two is not equal to 0. So it's actually saying the same exact thing in a different way. So we will, using this one sample t-test, we will actually calculate the statistics, and we will check if the mean of the group is actually in the rejection region or the acceptance region, and then we claim that we accept the null hypothesis or reject the null hypothesis. The test statistics we use for this is actually t-value. We calculate the t-value using the formula that you see on the screen. In this one, x hat is actually the mean of the sample group, because we are talking about one sample. So we have only one sample anyway. So we are, again, x hat is the mean of the sample. Mu here is the population parameter or the standard value that we are going to compare. And S is the standard deviation of the group or sample, and N is the number of people in the group. So this is the formula that we use. So how are we going to decide this one? And I would like to do it with an example together with you. And after the example, I'm going to give you the tables that we get from the SPSS, and then together we will interpret it. Let's say, as an example, we want to explore if the international business course grade of the management students is different from the university mean, which is 50. Where did I get this 50? 50 is a historical value. It was always like this, and when I have the average of all the population in the past, I reach 50. And I'm trying to understand if this year students having a mean different than 50. So when we see it, it's only one group. We have only one group of students and one standard value, which is the population mean. So we will just end up, okay, we have to use one sample t-test. So our null hypothesis saying that, okay, this grade mean of this group of students is not different than 50. So our null hypothesis actually claims equality of these two values. And our alternative hypothesis is actually claimed the opposite. No, they are not the same. Actually, the mean grade of the students is different than 50. So we need to go to SPSS and conduct the test. And when we conduct the test, we have actually two tables for this test we have from SPSS. And again, if we have time, I'm going to conduct the test on the SPSS. And the first table is actually sample descriptive statistics. And as you see, international business grades, there is a mean, standard deviation, and the error. When we see that, the mean is actually different from the 50, right? But just please be careful. This just descriptive statistics table. We don't make any decision on the hypothesis just looking at the mean. The point that the difference, we are comparing it with the number 50. This difference is actually significant or not. This is our question by looking at the test table, which is also provided by SPSS. I would like to draw your attention in two cells here. The one is mean difference. Mean difference says that is 2.405, meaning that international business grade mean actually 2.4 higher than the university mean, which is our test value. It's 50. So we know, but the question is, again, if it is significant or not. To make this decision, we go to this second cell, which is significance. We compare the significance and check the significance is less or smaller or greater than our significance value. As you would remember, significance value actually is 1 minus confidence interval. For 95% confidence interval is going to be 0.05. So when we compare this significance value, we see that it's smaller than 0.05. So when it's smaller than 0.05, we reject the null hypothesis, and it's a rule for us. Again, if significance, I would like to mention and highlight this point. In all tests that we are gonna do, it doesn't matter. It can be T, it can be ANOVA, it can be regression. If the significance value is smaller than our significance threshold value, which is 0.05, we reject the null hypothesis. And for this example, we will say that, we'll conclude that the difference between this student's mean and the value 50 is actually statistically significant, and thus they are not equal to each other. So this is how we make our decision, not looking at the descriptive statistics, looking at this significance value in this table. Because you will see in the other examples, sometimes although the means are different, but these different might not be significant. So we will claim that, okay, these means are equal to each other. So what does that mean? I see a difference, but it's not significant. It means that somehow by an error, by coincidence, we chose a wrong sample. So that's why we have this difference. But in this example again, because it's less than 0.05, we reject the null hypothesis and conclude that yes, the mean of those students are really different than university mean. We can check this also looking at the confidence intervals. As you see on the right side of the table, we have a 95% confidence interval threshold values for lower and upper. What do they mean? Actually, we can apply this here. When we check, our mean is 52.41. So what we should do is we should subtract this lower level value from our mean, and upper level value we will add to our mean. So we end up with our confidence interval. So our confidence interval is between 51.5 and 56.31. If our test value is between this confidence interval, we would say that yes, our mean is equal to the test value, and the difference is not significant. So there is two ways of checking this, but the best and the easiest way to check the significance value and to see if it is smaller or if it is greater than our threshold 0.05. Let me give you the example of, I'm going to come back to this one, paired samples t-test. Paired sample t-tests is a very similar, but in this time, we compare the means of two different groups on the same variable. Right. So this usually a kind of repeated measure. Again, these are the formulas of the statistics, and I'm not gonna go in detail. The same rules apply. I'm just gonna give you an example to make you understand what is paired test, what is paired sample t-test, and how we're going to conduct. This example actually saying that now we want to explore if the Math 1 grades, let's say it's the midterm of the Math, and the Math 2 grades, it's the final grades of the same students, bachelor semester 2 students. So we have one group, actually, we have the same group, or we can say the paired group, and we are trying to compare two different versions or two different variables of the same group. Again, this usually we see it to how a variable changed in time or how a variable changed after some manipulation in the experiments, for example. Or let's say that we had the midterm grades, as we usually do. We try to give them some extra homework, some exercise and everything. And then we have the final exams. And now we are comparing these two, if there is any development or not. But the point here, we have one group and we have two variables belong to the same group. So it means that we have to use paired sample t-test. So our null hypothesis is saying that these two variables are equal to each other. These actually two variables of the same group are equal to each other. And the alternative hypothesis, of course, claim the opposite. No, they are not equal. So when we apply the test, these are the tables that we receive from the SPSS. As you see, SPSS provides us, again, with simple descriptive statistics. And in this table, it gives us the mean. Again, we see a different mean from the Math 1 grade and Math 2 grades. Okay, from here, we can claim, but one more time, we don't make any decision by just looking at the descriptive statistics table. Another table that SPSS provides us with the correlation between these two variables. Actually, correlation gives us an idea, but it doesn't give anything related to the difference between the two. It just gives us, okay, for example, in this one, we have a slight positive correlation, meaning that both grades change in the same direction. However, we make our decision by looking at the test table. This is the test table for paired samples t-test, actually. Again, when we look at this table, we see the mean difference is minus 635. What minus means here, meaning that the second variable is greater than the first one, because the system calculates the mean of the first one minus the mean of the second. So if it is minus, it means that the second one is higher. So in this example, Math 2 grades, which is the final grades, are higher than the midterm grades. So the second point is if this difference significance. And then we go to the significance cell, we see that it is smaller than our threshold value, which is 0.05, means that we reject the null hypothesis and claim that the difference between these two means is statistically significant. And it means that whatever we did between the midterm and the final exams helped the students increase their grades. So this increase is actually significant, and there is a difference between two variables that we do. So as you see, now we have one group again, but we tested two variables or the two versions of the same variable in time belong to the same group. So the interpretation is very similar. We just check the significance and we made our decision based on the significance value. The other example is actually independent samples t-test. And now we are talking about two independent groups, and we are going to compare the same variable of the two different groups, actually. Again, all other things are very same. I prepared this PowerPoint because I'm going to share it with Dr. Vladimir to put. If you want to check it afterwards, you can go through all the details. But I want to directly come to the example. In this example, now we want to explore if the accounting grades are different from the students coming from state high schools or private high schools. Now we have two different groups, right? We have a group of students coming from state high schools before the university, and we have a group of students coming from private high schools before the university. Now we have two different groups, but we have one variable. We have accounting grades average. So the null hypothesis for this example saying that accounting grade mean is not different for the students coming from different high schools, or alternative hypothesis saying that no, it is different. So again, we have two groups right now, but one variable. Of course, we are going to go with independent sample t-test. So interpretation of this is a little bit different. Actually, the same logic, but the table is a little bit different. Again, the first table comes to us is descriptive. In this one, we see that the state and the private, the accounting grade of the students coming from state high school and the private high school. When we see the mean, actually are again a little bit different, but we don't know if this difference is significant or not. And then we are going to the independent sample t-test table, which is a little bit more complex compared to the other ones. So I would like to a little bit make it bigger for you to see it better. In this table, actually, we have two parts. The first part is the green part that we call Leven's test for equality of variances, and the second part here is the t-test table. Before reading the t-test, specific to this test, first we need to check the variances are equal or not by looking at the Leven's test. And again, we are checking the significance. If the Leven's test results significance is less than 0.05, then we conclude that the variances are not equal. It's the same exact logic that we used before. And if the significance here in this green one is more than greater than 0.05, we say that yes, the variances are equal. Okay, what's going to change when we make this decision? As you see from this table, there is two lines of t-test results. The upper line, as I just showed it in yellow brackets, yellow square, highlighted with yellow, is the line that we should read if the equal variance is assumed. And the blue one is the line that we should read if the equal variance is not assumed. So there is two lines for t-test result. And as you see, there are different significance values, so we need to be careful to go to which line. So for this example, Leven test, as you see, is smaller than 0.05. It means that the variances are not equal, so we need to go with the second line, which is highlighted with blue. So now we are going to interpret our hypothesis reading the blue line. And when we read the blue line, we see that significance value is 0.03, which is less or smaller than our confidence interval threshold value, which is 0.05. So it means that we reject the null hypothesis and we conclude that this difference between two means is statistically significant, and thus the means are not equal. If the variances were equal, we would go with the upper one, and then because this number 0.07 is greater than 0.05, we would say that yes, although the means are different than each other, but this difference is not statistically significant. I hope you got the idea of how we interpret the tables and the slight difference between these three different t-tests. And I would like to summarize the ANOVA tests. Again, I want to go a little bit faster. And the difference of ANOVA actually, now we are trying to compare three or more groups, or three or more variables. Okay, so the only difference than the t test, actually, of course, there is a calculation difference because ANOVA is using F statistics rather than T statistics and on the calculation and mathematics side. But as a concept, the difference is now we are talking about the comparison of 3 or more things. So if you have only 2, you will use the appropriate t-test. If the comparison is among 3 or more groups or variables, we will go with the ANOVA tests. Now our null hypothesis saying that all means are equal, and the alternative hypothesis saying that this equality is not achieved. So not all the means are equal. Here is a point that I would like to highlight. It doesn't mean that every mean is different than each other. It means that at least one mean is different than the others. So please be careful here. If you reject the null hypothesis, it doesn't mean all the means are different. It means at least one of them is different than the other. So please perceive this in this manner. So what does it mean actually? If we accept that all means are equal, it means that there are, let's say, 3 here. All 3 distributions are almost on the same mean. If we reject the null hypothesis, it means that either one of them is different or all of them are different than each other. There are these calculations here. I'm not gonna go through it because unfortunately we don't have enough time. But again, this ANOVA is being calculated by considering the differences between groups, I mean variations between groups and the variation within groups. So when we talk about the variation between groups, we are talking about, I can explain it on this graph. Each group here, as you see, has its own mean, right? For example, for the first group, it's x hat 1. For the second group, x hat 2. For the third group, x hat 3. And all these have variations when it is compared with the population mean. So this gives us the variation among groups. And there is another concept, variation within, right? What does it mean? It means that the variation of each data or difference of each data compared to the mean of their own group. So, for example, in the first group, the difference of this data from its own mean. For the second group, for this data from its own mean, and so on. So there are 2 differentiations that we need to consider. First is the differences or differentiation among groups, variance among groups, or the variance within. So actually, the statistics that we use in one-way ANOVA actually having the ratio of the mean square values of variation among groups and divided to the within groups. This is how it's being calculated. Again, the logic is the same. When we calculate the F value, if it is on the rejection region, we are going to reject the null hypothesis. The rest interpretation is exactly the same how we do. So let me go through an example to give you a better idea. Let's say that in this example, I want to explore if the economics grades of the bachelor student coming from different diploma programs, for example, management diploma program, marketing or HR, are different than each other. As you see in this example, I have one grade, economics grade, but I have 3 groups now. I have a group of students coming from management diploma. I have a group of students coming from marketing diploma. I have a group of students coming from HR diploma. So now we have 3 groups. So we need to go with the ANOVA. So I want to compare the economic grades, and probably you can do it in your surveys, in your research, for example, comparing a mean of a variable based on the education level, based on the nationality, based on the sector, all these things that you can compare using ANOVA. And then our null hypothesis saying that the means of all groups are equal, same, and alternative hypothesis, of course, saying that they are not equal. At least one of them is different than the others. So again, the tables from SPSS is showing the descriptives first. As you see, now the difference is a little bit different than each other. And we have a test of homogeneity of variances. Again, Levin statistics. In this example, our significance is greater than our threshold value, meaning that the variations are equal to each other, as we described. So it means that we can go with the ANOVA. If it is less than 0.05, it is smaller than 0.05, then we might go with some corrections for the data or using another test for our purpose. One of the non-parametric tests who can serve for the same purpose. And this is our ANOVA test actually. When we see its significance, we see that it's less than 0.05 and we reject null hypothesis, meaning that the economic grades are different among groups coming from different diploma programs. However, now we know there is some differences, but we don't know the difference is coming from which program, or all the programs are different. For that purpose, in the ANOVA, we apply post hoc tests. Again, to understand which group or groups create this difference and to see. For this one, we have a lot of different options for post hoc tests. And this is a post hoc test, let's say, window from the SPSS. As you can see, we have a lot of tests if equal variance is there, and if not, we have other tests. And for this example, we have equal variances, and I just apply 2K tests, which is one of the most common tests which are applied. And in this example, as you can see, table gives us the comparison of every pair. It compares with the management with marketing, management with HR, marketing and HR, all possible comparisons in the table. And if the significance value is less than 0.05, we can say that these are different. For example, in this first red line, we see that comparison of management with marketing and the significance is 0. So management students are different than the marketing students. But when we see management with HR students, the difference, the significance value is greater than 0.05. It means that the difference between management and HR students is not significant. So we see that as a conclusion, and we also see that marketing is different than management, and marketing students are different than HR students, and it means that this difference is created by marketing students actually. When we go back to main table, although our means are different for all groups, the ANOVA test told us, yes, the difference of marketing students is significant. However, the difference between management and HR students is not statistically significant. So as a conclusion of this test, we say that the average mean, the mean grade of marketing students is higher than the other groups, which we assume equal based on the ANOVA test. This is how we conduct the tests, and this is what t-tested ANOVA mean. Actually, we have 8 minutes, and I would just like to let me stop sharing my PowerPoint and try to share. At this point, is there any question? Because we have another session next week, and we can do applications of SPSS during that period, because we only have 5 minutes now. Even if I start, it's not gonna make any sense. So I'm gonna conduct the application on SPSS in the next session, and together with the other ones.
That will be helpful,
Yeah.
of course.
Sorry?
Be helpful. That will be helpful, definitely.
Thank you. Thank you, Dr.
Yes,
Yamin.
yes. Thank you very much, Professor.
Any other questions, my dear colleagues? So we, if you allow and if you agree, I'm gonna do the SPSS application in the next session. So we will have more time and we can go through much better the menus and the parameters. Okay. Thank you so much for your support.
Thank you very much.
Thank
Thank you very much.
Professor.
Very
Thank you,
informative.
Professor
Thank
Albert.
you very
Thank
much.
you.
Thank you, Professor.
Thank you so much, my friends. And
Thank you,
again,
Professor Alper.
thank you.
Thank you.
Thank you so much.
Thanks, Alper.
Thank you. Thank you. And hope to see you next week in our following session. Thank you and have a great day.
Bye-bye. Bye-bye. Thank you.
Bye.
Thank you, Professor.
Bye-bye.